Hello, welcome back. In this segment, I wanted to talk about a basic proposition we need for a couple of more segments. Let us assume that we are given a group G, finite group, and a group element small g with its order being I. It's the smallest value for which g power I is 1. That is the meaning of the order. We talked about it earlier. Okay. So the proposition is that g power x equal to g power y implies x congruent to y mod I. It is not only one direction, but it's also the direction. If x is congruent to y mod I, we can also conclude that g power x is same as g power y. I will prove this, but I wanted to first show you an example. Okay. So g power x is equal to g power y if and only if x is equal to y mod I. Let's take the example that we have been playing with. Take, for example, row 3, meaning the group element g is 3. Okay. Let's take two elements. For example, 3 square is 9. Right? And 3, 6, 7. 3 power 7 is also 9. So we have two elements. 3 power 7 is equal to 3 power 2. We can also conclude that 7 is congruent to 2 mod 5 because 5 is the order of the group element 3 because 3 power 5 is 1, right? So on the whiteboard, we used I being the order. I is 5 in this case because 3 power 5 is 1. And we know 7 is congruent to 2 mod 5 because 5 divides 7 minus 2. Okay, so we checked this example for G being 3. You can select any other group element and convince yourself that whenever you find two elements are equal, their superscripts or the power elements must also be congruent. But remember, the congruence here is with respect to the order of the group element you're picking. Okay, let's take some other example. What about 9 power 3? 9 power 3 is 3, right? 9 power 3 is 3. Okay. Anywhere else? 3, 6, 8. 9 power 8 is also 3. And we can easily see 8 is congruent to 3 mod 5. 8 is congruent to 3 mod 5. All right, so we are able to convince ourselves that this theorem is likely true. Now, when we will prove it is true, in fact. But I just want to give you an example, okay? Okay, so I'm going to take the forward direction. Assume g power x is equal to g power y. Then I can multiply both sides by g power minus y, which exists in a finite group. Therefore, I can rewrite this equation as g power x minus y equal to 1. In the previous segments, we proved that computing g power x is same as g power x mod I. So in the place of x, we have x minus y. So I can replace the power by x minus y mod I equal to 1. Now we need to do a little bit thinking. When you do mod I, what are the possible values? It can be 0 through I minus 1. But we learned that order of g is I. Okay, that means this value cannot be any other non-zero number. Okay, if it is a non-zero number, it will be less than I because that's how mod I is defined. But that will contradict the definition of order of a group element. Is g power I is 1, I being the smallest. That means this whole thing must be 0. If it is non-zero, it will be smaller than I, which is contradiction because I is the smallest element. So it has to be 0. So x minus y is equal to 0 mod I, which means same thing as saying x is congruent to y mod I. Okay, so we proved this direction. And what about converse? Let's assume x is congruent to y mod I. Because of the way congruence is defined, it's same as saying x mod I is equal to y mod I. Okay, let's take this example. 10 is congruent to 6 mod 2. This means 2 divides 10 minus 6, which is true. Okay, so 10 is congruent to 10 mod 2 is 0, 6 mod 2 is also 0. That's the reason why I say x mod I is same as y mod I. Okay, which means now consider g power x. G power x is same as g power x mod I because of the way exponentiation works in a group. And we proved here x mod I is same as y mod I, so I can replace this by y mod I. And we also know g power y is same as g power y mod I. Therefore, we proved g power x is equal to g power y. So essentially, if the powers are congruent, then you can convince yourself that g power x is same as g power y. If g power x is equal to g power y, you can also be convinced that the powers must be congruent. But the congruent modulus is the order of the group element that you're playing with. If the order of the group element g is I, then you can put a I here. That's this I must be the same as the group order. Okay, that's basically it. Thank you very much.